here's an application of function composition. We have some sales specials, either $15 off or 10% off. Our job for the first part is to write a function representing each of those. Okay, well, I'm going to let x be my original price. To represent $15 off, we're going to call that function f. It means I'm subtracting $15 from my original price. So simple function f of x is equal to x minus 15. Now we'll let g be the second one, which is 10% off. Okay, that means I'm subtracting 10% of the original price from the original price. Did you catch that? 10% of the original, so times, subtracted from the original. So it's going to be x minus 0.10x. Simplifies to g of x is equal to 0.90x. Okay, now what if we want to find a composite function that does first the $15 off and then the extra 10%. All right, so I'm going to start with my x, and the first thing I want to do is f and then g, so I'm working backwards. What I'm really looking for is g of f of x. Okay, g of f of x would be g of, well, what's f? X minus 15. Okay, and then what does g tell me to do? It tells me to take this x minus 15 and multiply it times 0.90. And that gives me 0.90x minus 1350. What if they say, no, we'll have you first take the 10% off and then the 15 off? Okay, well, this time the first thing I'm going to do is the g. So I would do f of the g of x, because the first thing you do is the one that's closer to the x. So f of g of x would be f of the 0.90x function, and f means you're going to take this guy here, whatever's inside, and subtract 15. Now, if I could talk them into it, I'm always going to ask them to take the percentage off and then the dollar off coupon. That's not usually the way they do it. They know what works better for them, so they're usually going to make you take the dollars off and then the percentage.